And this can be seen for the different measurements of the bulbs with different resistances. We have the 10 ohm resistance bulb and the 20 ohm resistance bulb. And the charging and discharging times are displayed here. For the 10 ohm bulb, we have a charging time of around 20.55 seconds and a similar discharging time. While for the 20 ohm bulb, we have a charging time of actually twice as high, with 40.42 seconds and 40.41 seconds. Finally, we come across the time-dependent voltage across a discharging capacitor, especially dealing with resistor-capacitor circuits. The way this was done was to first, in a resistor-capacitor circuit, actually charge our capacitor to its maximum voltage, unplug the battery from the circuit, and then just let it discharge, or the current discharge for 20 seconds until it reached approximately 0. Then I took the different measurements of the volts for each second for 20 seconds, divided each voltage measurement by the original, and took the natural log of the ratios of the current voltages divided by the original voltage, and ended up with a straight line with a negative slope of 0.166, and the predicted RC, aka time constant, was just the prescribed 0.2 farad capacitor times 30 ohm resistor, which resulted in a time constant of 6. And to get the computed time constant RC, you just had to divide 1 by 0.166, aka the slope, to get a time constant of 6.024, which closely matches the predicted measurement. Finally, we have the answers to the two questions at the end. If we were doing this lab in real life and use an actual emitter instead of an ideal simulated emitter, what's different about using a real life emitter? How would it have affected the curves you hooked it up to? The answer is ideal emitters have zero internal resistance, as I addressed previously, and therefore not considered in circuit calculations. Conversely, in real life, emitters have some internal resistance and are thus not ideal. Emitters in real life actually have a potential difference across it. The second question is that if we were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in this circuit, how quickly our ideal model will predict the capacitor to reach full charge? And will this prediction happen in real life? Explain. The answer is the capacitor would charge much more quickly and it would experience the quote full voltage of the circuit because there wouldn't be anything to impede the flow of current in the circuit. That's all. That's the overview of this lab. I hope you enjoyed it. Thank you for your time.